let's first talk about the videos that I have uploaded on the Canvas. It's very important that all of you have to pay attention to those videos, take notes, and make sure that you understand the content. Yes, you're welcome to turn your video on. No problems if you are comfortable. So we can see you. All right. Any questions on those videos? Basically, there are about set of 4 or 5 videos that we have uploaded talking about the heteronuclear diatomic molecules, such as carbon monoxide, cyanide, CN minus, right? Um, so the idea there is how do you combine the atomic orbitals of 2 different elements and arrange them in a molecular orbital picture, right? So that's what the purpose of the heteronuclear diatomic molecules is. Is there any questions on those? I think the examples of carbon monoxide and cyanide, right? Most of them. You should be able to write down the electronic configurations, be able to calculate the bond order, just like the way you have done for the homonuclear diatomic molecules in the previous class. All right. Any questions? Anything that was not clear? This is the opportunity for you to note down the questions while you go through the video and make sure that you get everything right. There's no point in asking me questions the day before the exam. You know that it doesn't work that way. Okay, I assume that there are no questions on those aspects. So we will now try to bring in a different type of heteronuclear diatomic molecule where things may be a little not so straightforward. So can you all see the board here, folks?
Yeah.
Can you see the board? All right, wonderful. Okay, good. So let's see. We'll talk about the molecule hydrogen fluoride, HF. Right? HF is a very simple molecule, again, heteronuclear diatomic molecule. How do we write the molecular orbital picture of HF? So what's the first thing that we need to know? The electronic configuration of hydrogen, which is 1s1, and the fluorine, and the valence shell configuration alone is going to be 2s2, 2p5. So if you now add the total number of valence electrons between hydrogen has only 1 valence electron, and then we have fluorine that has 7 valence electrons, 2s2 and 2p5. So the total number of electrons is going to be 8. Now the question is, how do we arrange the orbitals? So the first question that we need to ask ourselves is, between hydrogen and fluorine, which one is more electronegative?
Fluorine.
Fluorine clearly is the winner, right? That is the element in the periodic table that has the highest electronegativity value, which is almost a 4.0. All right. So what happens to the orbital energies when the atom is highly electronegative? Do they go down in energy or do they go up in energy?
Down in energy.
Go down in energy. Those of you who have seen the videos must have answered this question very quickly. Okay. That's the reason why we upload those videos, just to see how much you are following them. All right. So hydrogen is less electronegative. So the hydrogen 1s orbital will be somewhere here relative to the 2s and the 2p orbitals of fluorine. So that's my hydrogen. This is my fluorine. My fluorine has 2s and 2p. So 2px, 2py, and 2pz. There are 3 orbitals in the piece of shell oriented along the x, y, and z axis. Now, when you are combining the 1s orbital of hydrogen with the orbitals of fluorine 2s, 2p, which of these orbitals are allowed to be mixed based on the symmetry consideration, shapes alone? So if you look at S, it's spherical, right? So there is a 2s here that's also spherical. So you can have a combination of those two. And if you look at XYZ orbital, assuming that the bond axis, HF, is the Z axis, all right? So which orbitals of PX, P, and PZ do have symmetry compatibility that they can mix with F?
Is it PZ?
PZ, wonderful. So only PZ is allowed to mix because PX and PY do not have a symmetry compatibility. For those of you who are wondering about this, it's a very straightforward thing. When you have S, which is spherical, and a PZ, which is oriented along the molecular axis, there is an interaction, the constructive interference between the S wave function and the P wave function, right? But on the other hand, if you have PX or the PY, they are orthogonal to the S, which means they're perpendicular. For that reason, they cannot mix. So in the case of HF, then I can identify 3 atomic orbitals that can mix to give you molecular orbitals. One is the 1s of hydrogen, the 2s of fluorine, and 2pz of fluorine. So when you mix 3 atomic orbitals, how many molecular orbitals you are going to make?
3.
The number of molecular orbitals you make is exactly equal to the number of atomic orbitals you make. So in this case, although there are total of 5 atomic orbitals, only 3 of them have symmetry, adaptability, or compatibility. So for that reason, we're going to mix 3 of them. When you mix 3, you get 3 molecular orbitals. Now, what happens to X and Y? X and Y do not have any compatibility, correct? So for that reason, what happens is they remain as what we call non-bonding orbitals. We are now bringing in a new term. We heard about bonding orbitals. We talked about anti-bonding molecular orbitals. But here we have non-bonding orbitals because the PX and PY do not have a compatible orbital on the hydrogen to interact with. So they stay back like this. Am I making sense here, folks? Yeah? Now, you also find that the bonding orbitals are closer to the most electronegative atom, and the anti-bonding orbitals are close to least electronegative atom. In other words, the bonding is exclusively dominated by the most electronegative atom. The least electronegative atom does not contribute as much. Once we are done with this, then we can think about, there are about 8 electrons that needs to be accommodated. So 1, 2, 3, 4, 5, 6, 7, and 8. Am I making sense here? So this will be the electronic configuration. So in other words, there are 4 electrons on the non-bonding orbitals and 4 in the bonding orbitals. And the anti-bonding orbital is empty because we just don't have enough electrons. If we did have more electrons in the anti-bonding level, then the bond strength will be very weak. There will be no bond between hydrogen and fluorine. But we know that hydrogen and fluorine have a bond, and that is explained by the situation. Is this clear to all of you?
Yes.
Great, excellent. The other thing that I'm going to talk about is, remember in the past we used to say 1 sigma, 2 sigma, so on and so forth. But here we can't really use sigma terminology. Although some people use it, a sigma means it is cylindrically symmetrical. But because the orbitals have different energies, the molecular orbitals lack a cylindrical symmetry that is necessary for a sigma. But still, people, for the first approximation, they say it's 1 sigma, 2 sigma, 3 sigma. These are all sigma orbitals. And we have electrons in the 1 sigma and 2 sigma and the 2 pi x 2 py. And the antibonding orbital has no electrons. Am I making sense here? Are there any questions? So the examples that were given on the canvas had orbitals that are compatible on both sides. Sometimes you may get into a molecule where you don't have compatible orbitals, such as the case for the HF. In such a situation, we always go by the arguments of which ones can interact, how many orbitals we're going to mix, how many molecular orbitals we make, and orbitals that do not have a symmetry counterpart remain non-bonding. So we have bonding, non-bonding, and antibonding orbitals. Am I making sense? Anything that's not clear? So you want to copy that? The exact position of these orbitals, or whether this is up or down, you're not expected to memorize that, because those positions are given by the spectroscopy to see how many electrons come out with what energy. That decides the energy of it. So molecular orbital, this is a qualitative picture. Am I making sense here? So far what we have done is we have looked at homonuclear diatomic molecules. We also looked at heteronuclear diatomic molecules. We also looked at heteronuclear diatomic molecules that do not have compatible symmetries on both sides. Okay, so we covered almost all different situations. The next topic is going to be on polyatomic molecules. What happens if I have more than 2 atoms in a molecule? So polyatomic. Poly means many. Polyatomics means a molecule that has many atoms. How do we do this? So there are 2 ways of doing it. One is by symmetry, which we'll go into that very soon, what we call symmetry adapted linear combination of atomic orbitals. We have to go through a lot of introduction for that, so we'll do that. But we will now try to look at a strange but real molecule. That is, have you seen this? H3 plus makes no sense, right? Because we were told hydrogen makes only 1 bond. If hydrogen can make only 1 bond, there is no way in the world you can have H3 plus. But unfortunately, this species exists. How did they figure it out? They did an experiment where they passed deuterium gas on 2 Lewis acids, HF and SBF5. HF is a Bronsted acid, SBF5 is a Lewis acid. When you mix a Bronsted acid with a Lewis acid, you get extremely what we call super strong acids. When the deuterium gas is passed through this, they found a molecular species D2H plus. So D2H plus is very similar to H3 plus, because deuterium is just an isotope of hydrogen, right? So how do you explain the bonding now? The valence bond theory does not help us, because According to valence bond theory, hydrogen can make only one bond. So when you make three bonds, then obviously there is one hydrogen in the middle, which should be making two bonds. So valence bond theory is useless when you want to describe the bonding in H3+. So how does the molecular orbital theory go with this? That's what we're going to make a journey. Is this clear to all of you? Before we solve any problem, first of all, we need to understand what the problem is, right? That's what the statement of the problem is, just what I did. Once we have this problem, then we try to solve it. All right, so if I have H3+, hydrogen is 1s orbital. So when you have three hydrogens, we consider first one geometry where things are linear, H, H, and H. So the fact that it has a plus charge tells you how many electrons now this species has total.
Two electrons.
Where do we get two electrons? You're correct.
The two hydrogen.
There are three hydrogens, right? So totally, if they are neutral, then we should have three electrons. The fact that it has a positive charge tells you there is one less electron in this molecular species. So 3 minus 1 gives you 2 electrons. So we have basically, this is a 2 electron, 3 atom bonding. Quite interesting, right? 2 electrons are binding 3 atoms. Okay? So let's see how this happens. Now we have all 3 hydrogens are s orbitals, right? 1s, 1s, 1s. So when you mix these orbitals, how many molecular orbitals you get?
Should get 3.
Because you're mixing 3 atomic orbitals, we should get 3 molecular orbitals. So let's look at how these molecular orbitals look like. So the most bonding situation comes in when all the s orbitals have a positive sign of the wave function, right? So when you mix all 3 of them, the most bonding situation looks something like this. Plus, 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 and all 3 hydrogens are strongly interacting. That means the bonding case. Okay. In the next one, this is the one orbital, so we'll call this 1 sigma. This is the first molecular orbital we can think of because we have 3 wave functions positive. Look at this. The next one, yes.
It's kind of cut off.
Can you hear me now?
Yeah, I can hear you. It's just what you drew on the bottom is kind of cut off.
Oh, I'm sorry. Okay, let me put this up a little bit. Okay. Please let me know because I tend to think that whatever I see, you can see it. But if that is not the case, please let me know. Shout.
Yeah.
And I know. So this is what I was drawing there. So 3 hydrogens have a positive interaction. So that means the wave function is positive everywhere. Right? That is your 1 sigma orbital. Remember, there are 3 molecular orbitals. We have identified 1. In the next one, what happens is one of the orbitals is positive, one is negative, and in the middle is non-bonding. So in other words, you have 1 hydrogen atom plus, and the other hydrogen is non-bonding, and the second one is negative. This is your 2 sigma. In the 2 sigma, please understand that there is no bonding at all. This is a positive wave function, that's a negative wave function. They're far apart, and there is no bonding compared to the 1 sigma orbital. Okay, this is my 2 sigma. Now, the last orbital, the third molecular orbital, will look like one is bonding, one is negative wave function, and plus. So the interactions between these two are non-bonding. These two are non-bonding because the wave functions are opposite signs. So there is no way they can constructively interfere. They cancel each other. This is the most anti-bonding molecular orbital we can have in the H3 plus. We call that 3 sigma. Okay, so we now know 1 sigma, 2 sigma, and 3 sigma. So I'll just put them right next to each other. That's your 2 sigma, and 1 sigma is plus, plus, plus 1 sigma. This is the most bonding. There is absolutely no anti-bonding, but no bonding either here. And this one is 2 strongly anti-bonding interactions. Okay. So how many electrons? 1 sigma can have 2 electrons. 2 sigma can have 2 electrons. 3 sigma can also have 2 electrons. But the system has only 2 electrons. H3 plus has only 2 electron system. So we say the molecular orbital configuration of H3 plus is 1 sigma 2. Am I making sense here?
Yeah. You have the.
Probably that one there. Can you
Oh
see
yeah,
it now?
that's good. Thank you.
Good. Okay. Wonderful. Okay. Wondering, how did I come up with this choice? What exactly is the physical basis? All right. I'll give you an extremely simplified version of what we have just done here. You all have done in PChem particle in the box, right? So if I were to confine 3 hydrogens in a potential well, because the electrons have to remain among these 3 hydrogen atoms. They cannot stay above, way farther on the right or way farther to the left. They have to be in the middle. So the 3 hydrogens, if you have hydrogen, hydrogen, and hydrogen, the first one is a constructive interference of all 3 of them. That's how the wave function looks like. That is 1/2 of the wave. That makes sense? So the wave function everywhere is positive. So this is the most strongest bonding. In the next one, we have a plus, a minus. So this hydrogen is plus, this hydrogen is non-bonding, and this hydrogen is minus. Right? Now, in here, the wave function is positive everywhere, and it is not 0 in the middle. But here, the wave function is 0 in the middle. What do we call the point in which the wave function becomes 0? We have a name for it.
Node.
A node, N-O-D-E. In general, the more the nodes the wave has, the higher is the energy. This one will be lowest energy because there are no nodes. This one has 1 node. Now, if you go to the last one, we have something like this. We have a plus, a minus, and a plus. That's for the hydrogen, hydrogen, and hydrogen. So this is what we mean by plus, minus, and plus. Remember that the 3 sigma orbital has a plus minus plus configuration. So now if you look at this, this is a plus, minus, and a plus. How many nodes this has? The third wave function. The first one has 0 nodes. The second one has 1 node. And how many the third one has?
It is 2 nodes.
2 nodes. There are 2 places where the wave function becomes 0. So as a result, this has a higher energy. The more the nodes, higher is the energy. You can also understand because the wavelength here is smaller compared to this, right? When the wavelength is smaller, the energy and wavelength are inversely related. Smaller the wavelength, higher is the energy. Remember, E equals hc over lambda. So when the lambda becomes small, E becomes higher. That's exactly what's happening here. So your 1 sigma, 2 sigma, and 3 sigma. So even if you were to have multiple number of atoms, I just put it for 3, you can use this diagram to construct different types of molecular orbitals. Am I making sense here? Questions?
Yeah, I have a question.
Sure.
You said something about the wavelength, like the
Mhm.
smaller the wavelength, the
Mhm.
higher the energy, or okay, so it also has to do with the nodes then too. Like
That's
if it
correct.
has most more nodes, so a smaller wavelength and more nodes
Correct.
be the higher.
Exactly.
Okay, thank you.
Yes. Because if you look at this, this is 1.5 wavelength, right? Up to from here to here is 1 wavelength. And then I have another half wavelength. So this is 1.5 lambda. Now this one is 1 lambda, right? So this one, if you look at this, the total length is half lambda.
Okay, I see. Thank you.
So the smaller the wavelength, the more the nodes you have, and hence the energy. You also know E equals h nu, right? The Planck's equation, or E equals hc over lambda. As you shrink the wavelength, because this distance is the same, but the distance between successive crescent rows now decreases. As it decreases, the energy increases. Let's say in place of H3 plus, let's say if I have H5 plus 3. If I have 5 hydrogen atoms with 3 positive charges, you can still construct, right? The same way, instead of putting 3 hydrogens, you put 5 hydrogens, and the first one is always positive wave function. The second one will be like this. The third one will be like this, fourth and fifth. So this is how we can qualitatively construct the molecular orbitals for polyatomic molecules. But the issue is this. When they actually studied the molecule, H3 plus, spectroscopically, they found it's not linear. This is assuming that this is a linear combination. So now we have to look at why the system is not linear. Actually, it was found to be trigonal. So we need to look at the molecular orbitals in a trigonal geometry and compare that geometry with that of a linear geometry and argue why a trigonal geometry is more favored in H3 plus than a linear geometry. Okay? Am I clear up to this point?
Yeah.
What I'm not saying also is very important. If you now look at this one, there is no bond between A and C. Let's say we call this HA, HB, and HC, just to identify 3 hydrogens. In the first one, we have a bond between A, B, and C. So there is a bond between A and B. There is a bond between B and C, but there is no bond between A and C. If you now look at here, there is no bond between either A and B or B and C or A and B, C. In here, this is anti-bonding between A and B and C. That is the difference between these three molecular orbitals. I'm showing the same picture, but using different words to convey the same meaning. So let's now look at the other possibility, what we call the trigonal possibility. So now I have hydrogen atoms in a triangular fashion. So hydrogen A, hydrogen B, hydrogen C, HA, HB, and HC. So in a way, we can say if they're all positive, they're all interacting, this should be the lowest energy configuration. Okay. For now, I will call this 1 sigma. That's very similar to what we had in the linear combination, except that here I have bond between all three atoms, A, B, and C. The second possibility is I can have A in the middle, B and C. That is, and the third possibility is I have A minus B and C. So this is antibonding, that is antibonding. Okay. Now I have three of them, so this should be 2 sigma and this is 3 sigma. Here is a small issue. A sigma is like a cylinder, right? But this does not look like a cylindrical wave function. Can you all see this one, right? This doesn't look like a cylinder. A cylinder should look like this, plus, plus, plus. That is a sigma bond. This is not sigma. So instead of calling 1 sigma, we will call that A, the first state. And A or B is simply called singly degenerate. A singly degenerate means there's only one state that is possible because you can't have multiple states with 3 positives here. Okay. Now I'm going to argue that the remaining 2 states, although they look different, in terms of energy, they're exactly identical. Why? If you look at this, right, there is no bonding here, and there is one anti-bonding here. If you look here, there is a bond here, but there are 2 anti-bondings here. So what's the net one here now? 2 anti-bonding, 1 bond. So if you now look at the net effect, you have 1 anti-bonding. That's exactly what I have here, 1 anti-bonding. So these 2 now have the same energy, 2 sigma and 3 sigma, and we call this set an E. E means doubly degenerate. That means there are 2 states that have the same energy. That's what the word doubly degenerate means. So as we learn more and more, there'll be triply degenerate ones. They're called T's, and E means doubly degenerate. A or B generally is known as singly degenerate. Okay. Now, which one will be the most energetic configuration here? Which one is the strongest bonding that you see between the 3 of them? Most favored bonding is when all the wave functions are interacting with each other. So this state A is the most favored bonding state. So the electronic configuration according to molecular orbital theory for this is going to be A2. There are 2 electrons in the A state. Am I making sense? So basically what I have done is, when it was linear, right? The H, A, B, and C, the bond angle here is 180, correct? In a linear molecule, the bond angle is 180. When you make it trigonal, what you're doing is, you are reducing that bond angle from 180 to 60. Does that make sense? That's the only difference between the trigonal configuration and the linear configuration. In linear, the bond angle is 180. In trigonal, we have the bond angle of 60 degrees right there. So as you bend this molecule, you get from a linear to trigonal configuration. Am I making sense? So let's now compare the linear and the trigonal functions in terms of their energies. So let's now, on the left-hand side, write down the energies for the linear one. And on the right, we have the trigonal one. In linear, we have 1 sigma, 2 sigma, 3 sigma. In the trigonal, we have only 2 states. One is A, the other one is E. Right? Now, from linear to trigonal, we said for linear, the bond angle is 180 degrees, and for trigonal, it is 60 degrees. So, if you now look at the placement of the orbitals, the 1 sigma is placed slightly higher than A. So, as you bend the molecule, the energy of the 1 sigma comes down to A. The A is located at a lower energy compared to 1 sigma. Now, the 3 sigma and 2 sigma combine together to form the E. Remember, these are discretely singly degenerate orbitals in the linear, but when you bend it, you get a doubly degenerate level. So you go from 2 discrete energy levels to 1 energy level. The problem then is, why is this A at a lower energy compared to 1 sigma? To answer that, we got to look at the 1 sigma. 1 sigma is A, B, C, 3 atoms, all positive. In here, there is a bond between A and B, bond between B and C, but there is no bond between A and C. On the other hand, if you look at A, it has A, B, C. So there is a bond between A and B, A and C, and B and C. So this is most favored bonding situation because all 3 atoms are bonded in this configuration, while here we have only 2 bonds. So if we now look at the degree of bonding, the strength of bonding is much higher in this case, and that is the reason why H3 plus adopts a trigonal configuration rather than a linear configuration. In linear, the bonding is not as strong as it would be if this were to be a trigonal geometry. Does it make sense?
Professor, the only thing I don't understand is, wouldn't the protons repel each other more if they are in a trigonal fashion? Like if they're trigonal?
Okay, here is the thing. There is a bonding, right? The electrons are bonding, and there is a positive charge, right? So that positive charge and the negative charge of the electrons give you the Coulombic stabilization. This is not as stable as a proton. Please understand that. But still, it does exist. Does that make sense? H3 plus is not freely stable molecule, no. It forms under certain conditions. And those conditions are very extreme. So in Mother Nature, if you ask me, we don't have too much of H3 plus. Only in the laboratory, under certain conditions, we can make this species, which makes it, fairly metastable compound. But the fact that three hydrogens come together and form a species is very intriguing. That's what we're trying to answer. That makes sense, Dilya?
Yes, thank you.
Other people.
I just want to make sure I have this right.
Sure.
You said on one sigma, basically, does it have to do with its orientation? Like if it's linear, like A and C don't have a bond together,
Correct.
like they don't
Correct.
share a bond. And
Right.
then on the 60, the trigonal one, they all share bonds with each other. So therefore it has the
Much more stable.
stronger bond. Yeah, it's more stable. Okay, thank you.
That's correct. You got that right. Such diagrams, which depict the energy as a function of bond angle, are called correlation diagrams. So this is an example of a correlation diagram. Basically, a correlation diagram tells you what happens to the relative energy of the molecular orbitals when you change the geometry from a linear to trigonal. Of course, there are two ways of doing it. You can do it mathematically, or you can also do qualitatively, which is what we are doing in the inorganic chemistry class. All right, does it make sense? Questions? So we covered quite a bit. We talked about heteronuclear diatomic molecules, HF, CO, CN minus, and all that stuff. And then we also looked at an example of a polyatomic molecule, such as H3 plus. Now the question comes to our mind is, what happens if I have formaldehyde, HCHO? This is 4 atoms. Some molecules have 6 atoms. PCl5 has 6 atoms, right? So, or some NH3, for example, has 4 atoms. How do we deal with them? How do you write the molecular orbitals? For H3 plus, it's simple molecule, it's easy. But as you go into more polyatomic atoms, polyatomic molecules, then a simplistic approach like this can be very complex. So we will address that from the perspective of what we call symmetry adaptation. Here is the key. The orbitals have their own geometry, like S is spherical, P is dumbbell, D is double dumbbell, so on and so forth. And the molecules also have their own symmetry. Some are C1, some are C2, some are C2H, some are C2V, C3V, D3H, different point groups. Did you all learn about point groups, folks, in the inorganic chemistry class?
Yes.
Those of you who came from the other section, did you get enough instruction on that? Suppose if I draw a molecule, would you be able to tell me what the point group is?
Oh, yes. The functional group?
Okay, let me put a small thing like this. Let's say I have BCl3. What's the point group symmetry of this molecule?
The symmetry?
Mhm.
C3.
We have two sections, two types of students here. From my class, I think we have gone through this in quite a sufficient detail, but we also have half of the class coming from other sections. I just want to make sure that we are on the same page. So what's the point group on BCl3? Ryan? Or Anthony Lopez, would you like to make a comment? What's the first thing that we need to do when we are given a molecule and asked to write the point group symmetry? The first thing is we need to write the Lewis structure of the molecule, right?
Yeah.
So when you write the Lewis structure, you will find it's B and 3 Cls. Each chlorine has 3 lone pairs. Boron has no lone pair. It has only 6 electrons around it. It's an octet deficient molecule.
So it gets two lone pairs.
Which one?
It gets a lone pair, don't it, to be?
No,
No, because there are not enough electrons.
it already maxed out.
Two, it has 6 though, right?
Boron has only 6. So this is what we call electron deficient molecules or octet deficient molecules.
Okay.
This is an octet deficient. Sometimes you may have octet expanded molecules. This is an octet deficient molecule. That means it does not have an octet. The next thing is, what is the highest fold rotational axis of symmetry for this molecule? Ryan? Ryan Heston, do you understand my question, right?
Could you say it again?
What is the highest fold rotational axis of symmetry for this molecule?
I have no idea.
Perpendicular to the plane of this molecule,
Hmm?
through the center of this molecule. This is the real.
Could you please identify yourself? I can't see your name here.
Say that again.
Ryan, I'm looking for what is the highest fold rotational axis of symmetry this molecule has?
I have no idea. I literally just got back from the bathroom.
Okay, how about Anthony Lopez?
I don't know about rotation. I forgot about it, honestly.
Is anyone Shivani Shah? Do you remember?
No, I don't remember either.
How about Yulitsa Tapia? Do you remember?
I sure do not.
What is it? What is the highest fold rotational axis of symmetry this molecule has?
I'll take a guess. Would it be 120 degrees?
180.
120 degrees is correct. That's the bond angle. But if you were to rotate this molecule in a way that you end up with a similar looking configuration, you need to rotate it by 120, right?
Yeah.
And that angle, that axis has to be perpendicular to the axis of the board.
Uh-huh.
So 360 divided by whatever angle that you need to rotate by is what we call the order of rotation. So 360 divided by 120 is what?
3.
3. So we say the C3, that is the highest order rotational axis of symmetry. Okay. And then we have the BCl bond as a C and a C3. So what is the point group of this then? Medina, do you ranking there?
What did you say? I was writing my notes down.
Okay, but have you seen this rotational axis symmetry and point
Oh,
group?
Yeah, I have seen it. Yeah.
Okay, what is the point group of this molecule? We have C3 and 3 C2s, and there are 1, 2, 3 reflection planes In addition, we also have a reflection plane in the molecule. So there are four reflection planes, and three C2s and a C3. So what is the point group? Have you done this in your class?
I wasn't very good at it. No, I'm not really.
How about others from that class, from Professor Lu's class? And those of you who came from my class are very familiar exactly what this is. We have done quite extensively this stuff. Other people.
Well, when we had Dr. Lu, or at least when I had him, he
Mhm.
didn't really he went over this, but it was for a very short period of time. So
If I were to tell you that this molecule is D3H, would that make sense to you? Point group classification. Have you done the chart? Taking a chart and then looking at all the symmetry elements or symmetry operations?
Would there be like an SN, something like that?
SN, no, this molecule does not have SN. A D basically tells you that you have a C3 and three C2s perpendicular to the C3.
In case people need to know, it's on page 209 in the textbook.
Ashley,
Thanks for that, whoever that was.
I don't really know like what you're talking about. I know the C3 stuff and the vertical and horizontal stuff, but anything past that, I don't really know any of that.
have you heard of this word D3H?
I don't remember it.
How about other students in the class?
Wouldn't it have like 3 OV or something like that? And then the S3 axis?
There is no S3 in this molecule.
Yeah, then I don't know.
The problem is this, unless we know the point groups, we will not be able to move to the character tables. Because other students who are in my class have done this extensively. Gurveer, do you remember all that stuff?
Yes, I do.
We have done quite extensively, right? I mean, all this stuff. Suppose if I have NH3 or maybe simply we'll take water. So first you got to write the Lewis structure and then find out the geometry. And then once you have the geometry, then you should be able to identify the symmetry elements in this molecule. So Paula Vasquez, do you remember what the point group of this molecule is? Are you there, Paula?
Yeah, no, like if we try to find out like the symmetry elements, I think I can do that, but then I don't remember how to like assign the point group.
So what are the symmetry elements in water molecule, let's say? What's the highest fold rotational axis symmetry water has?
Is it 180? Well, is it 2?
Yeah. Where is that?
It's just through the oxygen.
Right, that's your C2 axis, right?
Yeah.
And it has a plane of symmetry, which is my hand perpendicular to the board. And then I have plane of the molecule itself. So there are two sigma V's and a C2. So the point group of this molecule is C2V. What I will do is I will upload the videos on the symmetry and point group classification, okay? In the next 24 hours, you will see those videos, because it's very important that all of you have to be on the same page in terms of identifying the point groups of molecules. Even if you have not learned in the previous class, that cannot be an excuse for not learning now. And I'm going to, we can't give those lectures again, but for those of you who are not familiar with the point group classification, we will upload. And Gurveer, can you please check if we have any symmetry? I think you sent me one, right? So I will look into other things too, and then I will put that one. It's very important that you need to have point groups of C2V, C3V, D3H, D4H, CS, CI. So many point groups we have done, right? So, and each point group will have a table, which we haven't talked about, but we will talk about that. These are called character tables. And once we understand the character tables, then we will be able to use the character tables to see what type of orbitals can we bring so that they can interact. So the molecular geometry dictates the orbital combination. So that is a huge topic that we need to talk about. So for that, the introduction is in inorganic chemistry. So please go over that. What we will do is this Thursday, coming Thursday at 2 o'clock, we will have in-person lecture, or in other words, virtual lecture. So I will be joining the Zoom meeting. I'm a little scared to see that some of you are not remembering what you have learned in the previous class. Okay, so I will upload those videos. Please watch them carefully. And there are other videos also on YouTube. You can find them, point group classifications, and you must master them in next 48 hours. So that when we start working on the character tables Thursday, you will be up to the speed. Am I clear, folks? Is that okay? Because I don't want to go over the character tables now if you haven't heard of these point group classifications. But on the other hand, if some of you want to have a private time, you really want to learn, we may have to set up another time, not during the class time, but some other time to have a Zoom meeting so we can go over that. I'm willing to do that, no problem. Okay, folks? Questions?
Yeah, so Thursday you said 2 o'clock?
Yeah, Thursday, 2 o'clock, yeah.
And that's
Is
Zoom
that okay?
meeting?
Yeah, Zoom
did you
meeting.
say that's in person or a Zoom meeting?
Zoom meeting, no in person.
Okay.
This class is entirely remote. That's what I was trying to explain to Ryan. There are 4 different classes on this campus, okay? One is called PPR. That means person-to-person required. So for example, if you're doing a lab, right, that's the PPR class. You cannot do remote. You have to be in the lab. The other one is called PPO, which means person-to-person optional. That means you have a choice of coming to the class in person, sitting in the classroom and learning, or you can also learn from remote situation. That is called PPO. The third one is called the main course. The main course is basically you have to have the class at a particular time, even if it is remote. Like for example, when I said 2 o'clock, right? It must be at 2 o'clock, which is the main course. Our course is not 3 of them. It is called a special class. It's called remote class. A remote asynchronous. Asynchronous means it doesn't have to be synced with the class times. But I'm trying to do as much as possible with the class time synchronization. Okay?
Okay.
If you look at the catalog, that's exactly what this code says.
Okay, thank you.
All right. So would you all promise to me that in the next 2 days, you will go over the symmetry and master that and come back? Yeah? Because if you don't know how to classify the molecules, then whatever I tell you from character tables, it makes absolutely no sense. All right? Okay, so I'm going to now go back to my computer and then start working on the uploading of the files. I will try to get it done in the next 15-20 minutes. And you can now work on this too. All right, see you all Thursday again around 2 o'clock.
Bye, Chari.
Thank you.
Bye-bye.
Take care.